Welcome everybody to my today's talk on Diffuse Reflectance Monte Carlo simulation to assess the transit time error in intraoperative fluorescence angiography. My name is Adi Naber. I'm from the KIT in Karlsruhe, and this work happened in cooperation with Jason Tchaikovsky from the McMaster University in Canada and Jaswin Jimmy from the University College Dublin in the Republic of Ireland. I'll be starting my talk from the very end of my title, so from the intraoperative fluorescence angiography. So what is it needed for? So angiography means we want to visualize vessels. So it's used in surgery to do a quality assessment to ensure a low recurrence rate after vascular surgery. In our case, particularly neurovascular surgery. And it can be used in the OR, so intraoperatively to check the vascular function. So what is used right now? First of all, the ultrasound flow meters, which you can see now to the left-hand side. It is an ultrasound transit time measurement technique. It requires contact, so you have a risk of contamination and mechanical stress on the vessels. For example, the vessel here shown right here, it's an artery, is around about 1 millimeter in diameter, and you of course need to have access to it. So what about fluorescence angiography? It's a non-contact method, and unfortunately until now no quantitative assessment of the vascular function is possible yet. You can see to the right hand side the current state, so this is what the surgeon gets from the system, so he sees the blood flows dynamic. So our goal is to enable a quantitative assessment of the volume flow. So what is the volume flow? So the volume flow is defined as the cross-sectional area times the flow velocity of our media. So if we dissolve it, we have a dependency on the inner diameter, the distance traveled, and the time needed for it. So you can imagine the distance traveled, for example, between the blue and the red spot, as well as the inner diameter, can be extracted from the frames, and the time can be extracted by matching the two signal curves, which are seen down here. So one crucial assumption is done in this case. So we assume the flow velocity is constant, or it is already the mean value over the cross-sectional area. So is this assumption valid for our case in fluorescence angiography? And it is not. We're in optics, and the photons have a limited penetration depth in both ways, so in the excitation and in the emission. So we will have a shift of our measured value to the ground truth. So what should we do now? So we want to compensate for it by introducing a correction factor, which is shown down here. Just to visualize it again, a small example with a small and a larger vessel. We have vessels of different sizes here. To the left-hand side, you can see the parabolic laminar flow profile, and in green the excitation photons, and in orange the emitted photons. So the arrows depict the, let's say, number of photons. So we will have a larger number of photons reaching areas close to the surface, and few of them will be reaching the backside of the vessel. And the same as well for the emitted photons. So the ones who are emitted from the backside of the vessel, they're quite unlikely to reach the surface and then be propagating towards the camera chip. And in larger vessels, we have the same issue. So the difference is we have a different, let's say, scan depth in our two vessels. So our flow profile in the right-hand side, we barely scanned until the middle of the vessel where the flow is the highest. And in the small vessel, we have a rather more uniform representation of our scan. So to summarize our problem, we have a crucial assumption which is not valid, which is that the flow profile is constant over our cross-sectional area or the mean value over our cross-sectional area. And the transit time error is depending on the vessel's geometry, as I showed to you in the example before. We have two hypotheses. First of all, the transit time error is depending on the vessel diameter, and the error shows a clear peak with a continuously descending arms to the right and left of it. How will we approach this? We will use a Monte Carlo multi-layer model to simulate the photon's propagation, combine it then with a fluid flow model to simulate the fluid's flow profile. In the end, we will convolve both to obtain a corrected volume flow. So first of all, the Monte Carlo model. So it is based on the Monte Carlo multi-layer model proposed by Wang et al. To the right-hand side, you can see a short overview, a sketch of the algorithm, which is not really surprisingly new. We have added two attributes to each photon or photon package. First of all, the maximum depth it has reached. It will be updated always if it's valid on the red dot here. And a binary flag indicating whether it is emitted back into the direction of initial incidence. The geometry is built up by 11% arterial wall, 78% blood volume, 11% arterial wall. This is relying on a mean value of arteries in the human body. We have launched 1 million photons, and our goal is to obtain a normalized probability density distribution of the deepest penetration depth of remitted photons. So what does that mean? We want to have to know where our remitted photons have traveled, and from this path we want to have the deepest point. And how will we normalize it? We will normalize it to the whole amount of photons emitted. So B of x are the counts of the photons, and x is the penetration depth. So our fluid flow model is assuming first of all laminar flow in vessels, which is a valid assumption. It will be also normalized to the mean flow velocity. The flow velocity in a laminar case is of a parabolic shape, so it can be described by the formula over here. And we have some boundary conditions, for example, at our boundaries of the vessel, so at the depth of 0 or the depth of the inner diameter, our flow velocity is 0, and we have a maximum of the flow velocity in the center line of our vessel, which is twice the mean value of the flow velocity. Considering those boundary conditions, we end up with this formula, and to the right hand side you can see the relative flow velocity on the x-axis, and on the y-axis the inner diameter in millimeters. This is depicting it for a vessel with an outer diameter of 3 millimeters. And in the end, we want to combine both of our models, so our flow velocity profile and our Monte Carlo model. We do convolve the probability density distribution and the flow velocity profile, and they result in a deviation of the measured flow velocity to the true flow velocity, which is based on our mean velocity. So you can see it over here. This is the transit time error, and since we are in a discrete space, we are having a convolution as a sum of the multiplication of each single elements. And again, x is representing the bins in the depth of the vessel, so going again from 0 to the inner diameter. So what does it look like after simulating it? So on the left hand side you can see first of all the probability density function with the probability on the x-axis and the inner diameter on the y-axis, and below it the flow profile, so the relative flow velocity and the inner diameter in millimeters. So what we end up with is, or what we do now is, as shown on the slide before, we're multiplicating each single element and summing them up, and in the end we get this table here, which is showing the outer diameter to the left hand side and the transit time error on the right hand side. And Visualizing it as a graph, we see here the outer diameter on the x-axis, the transit time error on the y-axis, that we have a clear peak and we have descending arms on each side. And this is also expected and was shown also in an experiment by Weichert et al. For fluorescence angiography, which have observed a pretty similar behavior. We still have a quantitative deviation from the experimental results, which are not surprising. The red bars here show or take out the values for the non-laminar case, which were done in this experiment as well. Okay, let's sum it up. Previous researchers have observed significant and diameter-dependent deviations of measured volume flow via fluorescence angiography compared to their reference flow, which was an industrial flow meter. We have identified that one source of error could be the faulty model, which we have presented at the very beginning, and we do propose an approach to correct for this faulty error. Our results match qualitatively with the deviations shown by this group, but not quantitatively. But this is not really surprising due to two reasons. First of all, we have no fluorescence events incorporated in our model. And second of all, we have a multi-layer geometry, which is not a good representation of a cylindrical vessel. So this also leads to our outlook. So we want to incorporate fluorescence in our model to indicate whether a photon has faced a fluorescence event or not. And further on, we want to convert the multi-layer model to a multi-concentric cylinder model with the inner cylinder depicting the blood volume and the outer ring, the arterial wall. And of course, in this case, we need to incident photons at different locations of our cylinders, since the geometry of incidence changes, which is not the case in a multi-layer model. So thank you very much for listening. I'm happy to answer any questions. Thank you very much. Further on, I want to thank the DAAD, the German exchange agency, which made the stay of Jason and Jaswin in our institute happen.